Okay, so first, my name is Qing. I'm first want to use this opportunity to introduce the agenda of today's workshop. Um, let me move this. So this is the second workshop from last year. Last year we created this workshop, also hold it in September. And in terms of generative AI, right, in the past several years, we have witnessed great exponential growth and great impacts of large language models to text-to-image diffusion type of models. And these models are typically very large. If you look at the GPT-4 model of OpenAI, right, the model size is 1.8 trillion parameters trained on very large data set. But the history of generative AI actually is not very long. So I shamelessly borrowed a figure from Mengdi, one of the speakers. So if you look at the history, it's only like 10 to 12, 15 years, starting from GANs and VE models, and really kicks off from ChatGPT. And now we have diffusion, DALI, GPT-4, and recently the Sora models for video generation. And the growth of the impact of generative models is tremendous, right? So one thing reflects the impact is that you can look at the stock price of NVIDIA. Like it's grown 10 times in the past several years. And people are even envisioning the generative intelligence from Microsoft, and the U.S. government is also considering regulating, considering the safety concerns of generative AI. So there's a tremendous challenges and opportunities in generative AI, both from theory and practice. So in terms of theory and optimization, right, so there's a lot of questions that how can we understand what generative AI is doing, efficient training, fine-tuning, control generation, unlearning and AI safety, and hallucination, and how to prevent model collapse, recently published in Science. And to scientific applications, right, solving inverse problems, building foundation models for PDEs, drug design, protein generation, etc. So in view of those challenges, opportunities, so we are organizing this workshop. So today we bring together like the leading expert in this field to talk about the practice and the applications of generative AI. And our goal is try to bridge the gap between theory and practice for scientific applications. And sorry, this is and by the end of the workshop, we will have a 1 hour panel, and we bring together both people from funding agencies and academia, try to discuss of the challenges and the future directions of generative AI. So this is the agenda of this workshop. So in the morning, we have 3 talks, and then we'll have 4 talks in the afternoon, and we conclude by a panel discussion. So without further ado, let me introduce first speaker of today's workshop. So for the first talk, it will be by Professor Mengdi Wang from Princeton University. Professor Wang is associate professor at the Department of ECE and Center of Statistics and Machine Learning at Princeton. She's research focus majorly on machine learning, reinforcement learning, and recently on generative AI. She received her PhD from EECS MIT, and before that, she received her bachelor degree from Tsinghua University. She received numerous awards. That is too long to talk here. So without further ado, let's welcome Mengdi to talk about controller generation for large foundation models. So welcome.
Okay, thank you, Qing, for the very nice introduction. And it's a pleasure and honor to be here and to mingle with Mida's faculty and get to know each other. Okay, so I'm a professor at Princeton focusing on basically generative AI. Okay, so I'll tell you a little bit about the AI initiative at Princeton later. So let's begin with research. Okay, so I myself, I was trained in control theory. So I'm a control theoretic. I would say I'm a control theoretically driven researcher in AI. Okay, so I wonder how many of you know about the book Out of Control by Kevin Kelly? No, I guess I'm too old. So this used to be like I would say a super popular book for I would say entrepreneurs like tech researchers. This was extremely popular when I would say when internet was taking over. Okay, so this was actually a very influential book. So in that book, written 30 years ago, the author Kevin Kelly already predicted that intelligence is going to emerge from a large number of connected, simpler units. So essentially, this book predicted neural networks. It predicted that by decentralization and by organizing simpler units together in sophisticated ways, higher level of intelligence is going to emerge, and the machines are going to become more like animals or even be better than animals. Okay, so it's a very insightful book written 30 years ago. Okay, so like if we look at what's happening today, so basically almost every single thing predicted in that book has become reality. Okay, sorry about this. Okay, but however, at the end of the last chapter of the book is about, hey, once all this like new advancement take place, so at some point, intelligence of machines are going to be superior to intelligence of humans. And the book ended up with out of control, meaning that the author couldn't figure out what will happen after that tipping point take place. And we are at this tipping point. Okay. So this announcement, not really announcement. So this like statement was made by OpenAI last year. Okay. So basically, I would say large language models or large foundation models more generally are already becoming much better than human beings in specialized tasks, and they're also becoming more and more generalizable. Right? So we are already at this tipping point when intelligence is getting out of control. And this is why OpenAI said that, hey, we need super alignment to making sure that this pre-trained monster of intelligence can be contained within the range of human values. Okay, so this is the problem of the so-called super alignment. Okay, so what people can do today are very superficial. Okay, so we can only talk about what people can do so far, but this is going to be a big problem in the near or even in the far ahead future. Okay, so how does alignment work? So the most popular, and this is like the go-to standard in practice, is reinforcement learning with human feedback. Okay, again, this is still being done on a superficial level. Okay, and this is already, I would say, like sort of like saving those tech companies from the scaling loss. I mean, we are expecting like GPT-5, we're expecting Q-star and strawberries, right? So the new technology there is going to be reinforcement learning from human feedback. Okay, and there's a long list of references to this. So the basic idea is once we have a pre-trained model, we can imagine my pre-trained large language model to be like my alien friend from another universe who's like a genius. Okay, so my alien friend has read all the human literatures, but he has never actually talked to a human. Okay, so your job is to teach your alien friend how to actually act like a human and interact with you. So this is the alignment problem. Okay, so the first step is to do supervised fine-tuning, okay, which is actually a must. Okay, and the second step is once my alien friend has started interacting with humans, right? So we want to build models to model the human preference. And the human preference are usually implicit. So the human preference, they might not be easy to tell from pre-training. So we want to build explicit models to model human preference as rewards. And the last step is once we have a reward, one can try to further fine-tune or adapt the pre-trained model to maximize or to align better with human rewards. So that's the basic idea. Okay, so this is a figure my student made, so you can tell it's less fancy. Okay, anyway, so 3 stages. Okay, so we don't really worry about supervised fine-tuning stage. But if we look at reward learning and the RL stage, actually there are tons of problems. And in practice, people try with different kind of like algorithms, models, people try to have different mixtures between SFT and RL fine-tuning, and people try to really work hard and engineer their data. So this is taking a lot of human effort to teach the LLM to interact with humans. Okay, so I will just mention a couple of like typical challenges with alignment, with reinforcement learning with human feedback. Okay, so one big challenge is like, I assume many of you have worked on reinforcement learning, especially when we think about alignment, we usually mean off-policy reinforcement learning. Okay, so we have human preference collected in some environment, and then we want to utilize those data to align my language model. Okay, so a big gap in reinforcement learning is distribution shift. And this gap is actually wider in the context of reinforcement learning with human feedback. So this is because we're not only trying to learn a policy in an offline way, we're also trying to model rewards. And the data distribution, the distribution of, I would say, state or context used for collecting preference data is usually different from the optimal distribution corresponding to my optimal policy, right? So this is an additional distribution shift from the preference data collection to policy optimization. Okay. And usually reward models are trained independently or separately, and there are like out-of-the-shelf reward models people can just take. But if we take an out-of-the-shelf reward model and try to use it to align, I would say, a new LLM, then we cannot really quantify the distribution shift. And this is going to basically mean that I might have poor coverage of the state space. But we still try to use a reward model, which is going to be actually overfitted to the actual distribution that we care about. And this is sometimes called over-optimization or reward hacking. Okay. Okay, so to look at this gap, we actually started with robotics. Okay, because even in robotics, reinforcement learning with human feedback is a pretty important topic. Because like if a robotics arms move there and there, actually sometimes we want a human to say, hey, I like to approach my bottle in this way rather than this way, right? We want a human to tell this, right? So it's actually typical to have a robotics to achieve the same goal with like different sequence of actions, and for a human to try to tell, hey, which does a human prefer to learn something implicit, okay? But however, even in the context of robotics, there's this pretty big gap due to distribution shift from preference data collection and policy optimization. So in those 2 examples, we actually were able to just benchmark the gap between the Oracle performance with the SOTA methods based on off-policy RLHF. And there is indeed a big gap, okay? So we try to solve this problem. So the basic idea for solving this problem is we want to make reward learning and policy optimization no longer independent. We want to do them together to try to mitigate the distribution shift. So we propose a bi-level policy formulation. So the basic idea is that we're trying to do reward learning on the outer level, and then we're trying to solve for an optimal policy in the inner level. Okay, so in this way, the 2 problems are coupled together. And as a result, we were able to, I would say, lower or like reduce the big gap of distribution shift. Okay, so again, we tested our method on those like robotics tasks, and we were able to see that, which one is ours? Yeah, so ours is the blue one. So you can tell like it's very obvious that if we try to couple reward learning together with policy optimization, one can do better. Yeah, this is actually very intuitive, and we're actually getting closer to the Oracle performance. Okay, and keep in mind that due to the nature of an off-policy learning problem, there's always a gap. Okay, but we want to get that gap to be minimal. Okay, so that's about policy distribution shift. Okay, so we have a follow-up paper applying this to LLM, but I don't have a slide for that yet. My student didn't report to me. Okay, so another problem with RLHF is how we model rewards. Okay, so this is actually like what like people at Google spend, I would say, half of their team working on, like trying to figure out better ways to collect data and try to have better ways to build reward models. So the simplest reward model is based on the Bradley-Terry model. Okay, so the model is going to be assuming that we have a single reward function, okay, and conditioned on a prompt X. So there could be two different responses, Y1 and Y2, right? And a human annotator is going to choose Y1 over Y2 with a probability following this particular model, okay? And here the assumption is that we have a single reward function R star, which is implicit, and one can estimate that reward using this model, okay? Okay, so this was also the motivation of the most popular algorithms, including direct preference optimization and PPO and simple and TRO, blah blah blah. Okay, so they all came from this model. Wait, sorry. Okay, so a big problem with this simplified model is it is assuming that all humans share the same reward function, or all humans share roughly the same reward function in expectation. Okay, so this is actually a pretty strong assumption, and it's definitely not true in practice. Okay, so in practice, we can imagine that people have different opinions and different preferences, and sometimes maybe the majority of people in this room, I don't know, really like coffee, but maybe one person really hates coffee, right? And we don't want to force coffee onto every single person. So, but what happens is like if we have a majority group and a minority group, so they could have diverse preference, or they may even have conflicting preference. Okay, but if we mix all their preference data together and assume that we have only one single reward, then my alignment performance after fine tuning, my model is going to be maximizing the interest of the majority group, and will be almost like ignoring the minority group. Okay. Okay, so we try to quantify a lower bound to quantify the alignment gap to show that there is an information theoretical lower bound depending on the, I would say, intrinsic diversity of my population. And this is something unavoidable. Okay, so again, this is like one example in which the minority and the majority, they might have different preference. And if in some case, maybe the minority group is okay with the preference with the majority group, then we can just do simple alignment and things could be fine. But in the second case, the minority group actually strongly dislike the preference of the majority group. And in this case, if we do simple alignment, the overall performance is going to be very bad to the minority group. Okay, so we try different like ablation studies by different percentage or ratios between the size of the majority and the minority group. And again, so basically like the more minority the second group is, the more minor they are, the performance just gets lowered. And this is something we definitely want to avoid when we try to provide an LLM to a general user. Okay, so the solution is very simple. So this is our paper we worked on it last year and got to ICML this year. So we actually came up with I would say, an unsupervised learning algorithm to infer the underlying user clusters based on preference data. And on top of that, we came up with a max-min RLHF method so that we want to make sure that we are going to pay attention to the minority group, or we are going to pay attention to the user group who is least happy with the LLM. So we can make sure that at least we're being fair and robust to different user groups. Okay, I'll skip this. Okay, so this is one example. So in this example, the majority group really prefers simple explanation on an elementary school level. But the minority group are like PhD students or professors who really like the technical stuff. Okay, so by doing max-min RLHF, you can tell that the response we got became like a relatively, I would say, like in the middle ground between a simple trivial answer and a super technical lengthy answer. So this is something that can be achieved by trying to tailor to both user groups. Okay, so we did a bunch of like additional examples with other preference data and other models. So in general, so if we do RLHF, by RLHF I mean like the standard RLHF with a single reward, then we are going to have this like pretty big difference between the performance on minority versus majority groups, right? But if we do max-min RLHF, then we're actually going to have very good performance from both groups. Okay. Okay, so far we were talking about alignment via fine-tuning. Okay, meaning that we have to come up with reward and then we fine-tune the LM using some sort of reinforcement learning techniques. Okay, so fine-tuning is going to be always take some time. It's always going to be costly. So a further question down the line is that, hey, what if we really want to adapt very quickly to different users, to different individual users? Okay, so we don't really want to fine-tune a model for every single new task or every single new user. Can we keep the weights but still achieve the same goal? Okay, so the next topic is alignment via control decoding. Okay, so it's still about control, but not control via fine-tuning. We are going to do control over the decoding process. Okay, so I'll speed up. Okay, so basically, whenever we try to run inference using an LM, so the response is going to be generated like token by token or word by word. And once a new token is generated, it's going to be fed as input to the transformer. So altogether, you can imagine like this is really a state transition process. It's a controlled system, okay? And blah, blah, blah. Yeah. So so this generation, this token by token generation process is referred to as decoding, okay? And one question is, okay, let's still try to do alignment, meaning that we want to steer the output distribution of the LLM to user preference. But can we do it via the decoding process instead of fine-tuning? Okay, so the answer is definitely yes. Okay, so again, the basic idea is that, hey, we want to have a token level Q function to tell me whether this particular token is good if we look ahead to towards the end of the generation process. Okay, so if we have the Q star, the theoretical optimal Q star, we can try to follow Q star to run decoding. Okay, so this is ideally what people want to do, right? If we have Q star, then we can run decoding to maximize Q star. And sometimes we always add a KL divergence as a regularization to keep my policy close to the reference policy. So we do not deviate too far away from the pre-trained model. Okay. And this can be done very simply, right? One can even like try to write down analytically what should be the decoding probabilities once we have Q star. So we don't have to fine tune. Okay. So the problem is we don't really have Q star. Okay. To evaluate Q star, we need to know the optimal state to token to token transition distribution, which of course is not known to us. Okay. So in practice, what people do is they don't have the distribution rho star, and they simply replace rho star with the reference distribution, which is simply the probability distribution of the output of the pre-trained model. Okay, so it's a simple proxy, and that's what people do. And so this was invented by Google, I think in 2023, but I think the paper got published this year. So it's called control decoding. Okay, and the gap is that, hey, we have this gap between rho pi and rho star. Okay, again, it's about distribution shift. So in order to reduce this gap, so one observation is that so there actually people have done a lot of work already. So there are a lot of like open source language models that were already aligned to different rewards. The alignment could have been done via fine tuning or, but they are already out off the shelf. Okay. So what we do is, okay, we're actually going to invite another aligned model as baseline. So we can transfer from an aligned model instead of transferring from the pre-trained SFT model. Okay. And I'm skipping all the technical details. So, but again, we ran a bunch of experiments. So our method is called transfer Q star, TQ star. Okay. And because we're actually using a lot more information from another aligned model, so you can tell that by leveraging this information in a smart way, we can do much better. Okay. And there are a bunch of like ablation studies in comparison to benchmarks, which I'm going to omit. Okay. So as we talk about control decoding, another very related problem is called speculative decoding. Okay. So when we think about alignment or control decoding, we were thinking about a single LLM. How do we tweak the token by token generation distribution? Okay. So speculative decoding is about having two LLMs, a smaller draft model and a larger model. Okay. So imagine that. So the goal is to really run user queries through the large model. But we want to minimize cost and inference time. Okay, so the idea is that, hey, what if, let's consider this large model to be like a PhD advisor, and we're going to get the advisor an RA. Okay, so we have a smaller model, and the smaller model is going to actually do most of the token by token generation. Okay, and we're going to, for example, generate 5 tokens, okay, using the smaller model. And then we're going to submit the sequence so far to the larger model for verification. But so the larger model can verify the previous sequence and the 5 new tokens using a single forward pass. Okay, so verification can be done very easily, not on a token by token level. Okay, so small model is going to generate token by token, and large model is going to verify every a few tokens. Okay, so one can try to like engineer a rejection sampling policy to make sure that the final output distribution is exactly the same as the original output distribution of the large model. Okay, so this is called speculative decoding, again by Google DeepMind. So OpenAI actually had a very similar paper around the same time. Okay, so this actually can save cost and accelerate inference by big time. Okay, so what we try to work on is we try to bring control into this. Okay, so instead of like heuristically just figuring out when to send the draft for verification, we try to train a control policy to predict in advance when my small model is going to get something wrong. Okay, so this policy shall be used to switch between the small and the larger model. So we can do the switching more adaptively by solving an optimal control problem. And we call this speculative decoding ++. And by doing so, we can accelerate any speculative decoding algorithm by, I would say, 10 to 12%. Okay, Oh, I need to say that by compared to the original baseline without speculative decoding, the overall acceleration can be from like 2 to 3 times. Okay, and we can do better than that. Okay, so far we have been talking about like control the generation process of large language models on different levels, on the level of fine tuning, on the level of token by token generation, and also on the level of like switching between different models. Okay, so I'm going to change gear because the topic I was supposed to talk about generative AI. So I'm going to change gear here, and I'll say a little bit about our work on diffusion models, and because I realized that the rest of the workshop is really about diffusion models. Okay, so when we think about diffusion models, we can still do controlled generation. Okay, so I mean, we all know diffusion model is the model that can generate images, videos, and protein structures. Okay, and diffusion models work by learning a score network to transform a noise distribution step by step into a distribution of whatever data we want to generate. Okay, okay. So as Qing just mentioned, like so, the idea of generative AI and diffusion models, they're actually pretty recent. But however, the very notion, the I would say the notion of generation, I think this probably came from variational autoencoders and and against generative adversarial networks. Okay, so at that time, so VAE is for data compression, and against is actually for discrimination. Okay, but the decoder and the generator, okay, from those two models, they turn out to be byproducts from, and those byproducts turn out to be useful and interesting to play with. Okay, so then people realize that, hey, I can actually use my decoder from my VAE to generate something. And then this generator from GANs can generate images that are actually better, right? So this was the time when like machine learning researchers realized that, hey, instead of clustering prediction, we can actually generate. Okay, so this was the beginning of generative models. And now when we think about generative AI, we usually think about this methodology that maps general noise distribution to general data distribution. Okay, but however, like diffusion models is pretty much a big evolution. So again, like putting on my hat as a control theorist, so diffusion models is not about figuring out a single mapping from noise to data. So it is about controlling a dynamical process with initial state being random to a limiting state distribution being the data distribution that we want. Okay, so here, the score network, either UNet, transformer, or whatever your favorite model is, this network we're learning here is really a controller of this dynamical system. So we are learning to control a process rather than learning the mapping of the process directly. Okay, so again, I'm going to go over this very quickly. So again, the idea was very simple, and the mathematics was like done, I think, like 40 years ago by probabilist. Okay, so we want to transform noise to data, right? Which is hard. What is simple is, if I start with data and I want to transform my data to noise, this is very simple, right? So the starting step is to figure out how to transform data into noise by simply adding white noise. And in order to make sure that the stochastic differential equation is stable and contractive, we can add a negative 1/2 there as a simple differential equation. And we can actually change the drift function to other things we like, as long as it's a contractive process with a limiting distribution being Gaussian. Okay. And then for any forward stochastic differential equation, we can actually use tools from probability to derive an analytical form of the time reversal. And this time reversal is what we want, the stochastic differential process from noise to data. Okay, and the drift function in the reversal process is actually what we want to learn. This is the so-called score function. Okay, and one can learn the score function by simulating the forward adding noise process and taking samples from it, and then doing supervised learning. Okay, and skipping all the details. Okay, so when we think about diffusion models, we actually care about what's going on, because we want to use diffusion models to generate not only artwork, but also drugs, proteins, materials. We want the model to be reliable. Okay, so this is why we actually want to understand the mathematical theory of diffusion models, why it can learn the underlying data distribution. And further, can we control the generation process further to align with what we want to achieve? Okay, so for the first question, first, let's be on the same page about that all the data we actually care about are low dimensional. Okay, so for example, if you look at this collection of images of teapot taken from different angles, right? If you think about those teapot images, they can be embedded into a circle, which is one-dimensional, okay? And researchers have done this very interesting analysis using manifold learning to approximately figure out the intrinsic dimension of ImageNet. Okay, they actually tried out other simpler data, but let's look at ImageNet. Okay, even for ImageNet, the intrinsic dimension is actually estimated to be 43, meaning that all the images from that data set can be embedded in a manifold of dimension 43. So the actual dimension is not that high, but we just don't know the structures of the manifold. Okay, so now we can make our question, we can ask a more concrete question, right? So let's think about the generation process of a diffusion model, which is this stochastic differential equation. Okay, and that score function in the middle is something we have to learn, we have to fit using a neural network. Okay, so the big question is, let's think about the stochastic process. The process is going to start with a random Gaussian or a random noise as initial point, and my random noise is going to be for example, in the high dimensional. For example, the dimension can be 3 times the number of pixels, right? So I have high dimensional noise, and my stochastic differential equation, which is estimated, has to be steering this dynamical process to eventually converge to an unknown latent manifold. Okay, so we want to study why this can work, especially if we're trying to learn this process from data, right? We want high dimensional noise to converge to a latent low dimensional manifold. Okay, so to study this, so we have to make some simplified mathematical assumptions. So one assumption we end up making is, I'm going to assume that my high dimensional data X can be embedded into a lower dimensional space. So phi can be a nonlinear mapping for that manifold. And A is going to be a matrix representing the latent representation of high dimensional data in the latent manifold. So that's part of the assumption. So another assumption is that I don't want to work with general neural networks, okay? Let's say that we start with UNet, which was the backbone for stable diffusion. So UNet is this multi-resolution structure with like conv layers and skip connections on every level, right? I'm going to simplify this to a single level, okay? So we're going to have a single residual connection from X to the output, okay? And also I'm going to simplify the conv layers into linear transformers, sorry, not linear, linear mappings, nonlinear ReLUs, and another linear mapping. Okay, so this is a simplified function class that we're going to work with, okay? And under these assumptions, we can actually derive a decomposition of the score network, okay? So this decomposition is actually pretty fundamental. So this decomposition is universal. We do not assume any distribution. We only assume that my distribution is supported on a latent manifold. That's the only assumption. And on this assumption, under this assumption, one can show that the score network, which is the drift function of my stochastic differential equation of diffusion models, okay, actually decomposes to one part which is on the latent subspace and another part which is orthogonal to the latent subspace, okay? And if we actually work out the math, what's going on is we can actually analyze this SDE. So the trajectories of the SDE can again be decomposed into two parts, which one is the projection on the latent subspace. Another one is the orthogonal parts. And the two parts are two stochastic processes. They are coupled together in some way, but the off-space error actually has a contractive nature. So this is a universal property for any diffusion models, as long as the true distribution has a latent low-dimensional manifold structure. Okay. So, and we can like generalize this analysis to general manifold, but it just takes a a lot more like nuances with dealing with curvatures. Yeah, okay. So what we could prove, this was a paper last year, was that we proved that diffusion models are efficient density estimators, okay? And I think the key point of interest here is that the convergence rate as a density estimator for diffusion models depend on little d, the intrinsic dimension of the latent manifold. In other words, what we prove is that diffusion models, training diffusion models naturally adapt to latent dimension of the higher dimensional data. So the convergence rate depends on little d instead of big D. Okay, and I'm skipping all the details. So the second topic is that now we want to further control the generation of a diffusion model. Okay, for example, in the context of protein, say that we have pre-trained my diffusion model to sample from the universe of all proteins, right? Now, in order to further control it, we want to generate a specific new protein structure with targeting a specific molecule. Okay. So I think a very, very interesting idea, which is actually like pretty transformative in the optimization community, is that we can convert every single optimization problem into a conditional sampling problem. Or in other words, every optimization problem can be a generative problem. Okay. So traditionally, as we think about optimization, we have some x, some variable we want to optimize, and we have some landscape, right, f of x. And usually we try to work with f, and we try to analyze the landscape of this optimization problem, and we have to come up with like certain algorithms or heuristics or gradient search or tree search or blah, blah, blah to find an argmax. Okay, so classical optimization is actually pretty powerful at leveraging problem structures. But classical optimization solvers, they are very, very poor in terms of leveraging data. Okay, but we can convert optimization into sampling. Instead of solving for argmax, we can say that, hey, imagine that we have this joint distribution between x and f of x. Okay, now can I condition on that? I want to condition on achieving a high value of f of x. Can I generate a sample of it? Okay, so now this is a conditional sampling problem. So the nice thing is that one can try to actually pre-train diffusion models or generative AI models a large amount of data of x. We don't even have to observe y, right? Because we know that diffusion models can learn the latent data distributions, right? So we can leverage data without we even think about the problem f. Okay. So this is really exciting, and in a paper we did last year, we formulate conditional diffusion for generative optimization. So this is really about trying to train a diffusion model based on a combination of unlabeled data x and the labeled pairs x and y. And the goal is to generate new x based on higher value of y. Okay, so again, there are several steps. We actually have to do reward learning, and this can be done with preference data, and then we have to train a conditional diffusion model. Okay, and then we care about what can we prove about this approach, because fundamentally we're trying to solve an optimization problem based on data. Okay, we care about the optimization gap. Okay, and again, so whenever we're trying to generate something new with a higher objective value, we are again introducing distribution shift. We are trying to shift the distribution of f of x from a lower value to a higher value, right? So fundamentally, there is a limit in terms of how much we can do based on the limited data we have. Okay, so again, apology for having a bunch of notations. So ignore all the notations. Okay, so in our paper, we actually work out the full set of optimization theory. We try to characterize the sub-optimality gap of using conditional distribution models for general black box data-driven optimization. Okay, you don't have to try to read the equation. I'm sorry that I didn't really talk about the notations. I just want to mention that, so this optimality gap, okay, is actually matching the mini-max off-policy banded optimization gap. okay? Meaning that diffusion models are efficient. They are as efficient as the best off-policy optimizers. And this is the best off-policy optimizer that knows the latent manifold. Okay, so this gap is a gap in the lower dimensional space. So in other words, diffusion models is implicitly a representation learner and an optimal off-policy learner. So we are solving two problems at the same time. And this is the power of like using diffusion models for data-driven optimization. Okay, so we had non-parametric results, which I'm going to skip. Okay, so this is a very simple numerical example we run on a control problem. Okay, so this is a problem in order to keep that single leg like hopping in the air. Okay, the reward is about like basically like how long this leg can stay hopping without falling on the ground. Okay, so because we're doing conditional generation, so we can tune the target reward, which is what we condition on. Okay, so we can tune that value to see how does the generated policy look like. So this works by like collecting a bunch of like off-policy trajectories from this control problem. Okay, training a conditional diffusion model based on all those data to model their joint distribution. And then we're going to condition on having a higher reward and higher value and generate new trajectories. Based on new trajectories, we can do inverse engineering to read off the policy. And here we are plotting the performance of the policy that we end up having. So I think the encouraging observation is that by converting this control problem into conditional generation, one can actually do even better than the SOTA off-policy RL algorithm. So in other words, so this is actually a simple generative algorithm not doing RL, not solving Bellman equations, not estimating Q functions. Okay, so this is an illustration that for some problems with, I would say, very obvious latent structures, it's sufficient to rely on generation. And people in robotics are actively trying to couple diffusion models with additional reinforcement learning to make things better. Okay. How much time do I have? Okay. So the last part is that in order to actually use diffusion for optimization, okay, we actually don't want to do this. So what I have here is like I would say like a framework to think about training diffusion models to model joint distribution between x and f of x. Okay, but this is actually going to be like pretty expensive because imagine that I might have, again, a pre-trained model on all proteins, right? But now I want to optimize for affinity. Then I have to retrain everything using the affinity label. Or maybe I want to optimize stability. Then I have to retrain again. We don't want to retrain my model for every new optimization problem. Okay, we want to be able to use a single pre-trained model and easily adapt a single pre-trained model to different downstream tasks. Okay, and we care, again, I care about the theory. My collaborators don't so much. Okay, so again, the idea is that let's look at the generation process. So this is the stochastic differential equation of the generation process, okay? So here, S theta is the drift function. Imagine that S theta is the network we have trained. Okay, so if we do conditional generation, what we need to do is we need to add Y, which is what we want to condition on, to S theta, meaning that we have to retrain the score function. Okay, so instead of doing that, instead of like retraining this drift function, we want to simply add an additional term as an additional control input to the decoding process. So the question is that, can I use the original pre-trained S theta and simply add another guidance term? And I want to know, would this work to solve my generative optimization problem? Okay. So this is known to work in the case of like classifier-based diffusion models, where the goal is to condition on a class label and generate new samples. But here our goal is more complex. We want to solve general optimization problems by figuring out this G. Okay, so again, so for everyone who knows gradient optimization, right? If I have a problem which is we want to maximize f of x, okay? And I have some process and I'm going to add something to it. So the natural thing to do is, hey, what if I just make my G to be the gradient of my new objective, right? Would this work? Okay, So since I'm asking this question, you can tell that this is not working. Okay, the reason it's not working is very simple, because we actually have to like spend pages of like proof to show that diffusion models can steer the dynamics from high dimensional noise to a low dimensional latent space, right? So now if I just add some arbitrary gradient direction on top of this nice process we have pre-trained, we're going to be jeopardizing the latent structure that has been pre-trained. Right? So whenever people do this, this is going to fail miserably. We cannot simply add gradients. Okay, so it turns out that we were able to engineer a specific guidance form, and this is actually closely related to a number of like empirical works who try to add smarter guidance to image generation problems. Okay, so I cannot go over the math, but think about this as another term which coming from proximal optimization. And in this particular guidance term, we are actually leveraging the pre-trained network so that the latent structure is preserved. And I cannot talk about the proof here, which is going to be too long. Okay. So basically, it's possible to add a guidance term based on first order information of a new objective function, but it cannot be the simple naive gradient ascent. Okay, so we figure out the framework of like adding gradient-based guidance to a pre-trained model, meaning that we don't have to fine-tune. We only tweak the generation process in a very lightweighted way in order to solve for a new optimization problem. Okay, and we were able to actually understand what's going on. So this actually works provably. Okay, so when we start with a pre-trained diffusion model and we add additional guidance to optimize for an additional objective function, we are provably guaranteed to find a regularized solution. So this is a simple case where we are going to be generating on average a regularized solution, which is not only argmax of f, we actually have a regularization term that is keeping my new samples proximal to the original pre-training distribution. And this is something this is a limit we cannot overcome, because whenever we generate something, we have to stay not too far from the pre-training distribution. Otherwise, the distribution shift will be too big and the methodology will be break. So this is the best one could do by only adapting a pre-trained model in the decoding process, by adding only an additional control term. Okay. So finally, so if we really care about finding global optimum, one can actually do self-improving of diffusion models. So this is done by not only adding guidance to the decoding process, but we also need to do weighted fine-tuning of the original score network based on self-play. Okay, so if we can retrain using self-generated data, okay, I'm going to skip everything. So the short answer is, if we can retrain and self-improve using self-generated data, this is going to provably converge to the global optimal solution of my optimization problem within the latent manifold of the pre-training data set. Okay, so this is basically the optimization theory for controlling diffusion models for generating solutions of optimization problems. Okay, so finally, I want to mention that when we think about guiding diffusion, so there's a very close analogy in nature. Okay, in diffusion models, somehow we can think about we have a random process, right, which is doing something already, and we are like tweaking some parameters to steer the distribution. This is very similar to directed evolution, which is what's happening in late nature, and this is how like scientists use to engineer proteins and other biologics. Okay, so actually by using ideas from online optimization, we proved why directed evolution with a machine learning model can provably explore in a genome sequence space or amino acid sequence space. And we were actually able to prove regret bounds for evolving genome sequences. And the similar technology, so we use the similar technology to design basically like guide RNA sequences for CRISPR-Cas12a. And we were able to actually improve the gene editing efficiency by more than 30 times than the original benchmark by doing AI-guided directed evolution. And finally, so this is part of a bigger collaboration at Princeton is, so we actually pre-trained language models for decoding messenger RNAs, and we're using it for generating novel mRNA designs. So our first paper was like published at Nature Machine Intelligence early this year, and actually we're pre-training larger scale RNA language models. And I want to say that so since this is about generative AI, so if we can think about generative AI as this powerful tool to leverage data, and on top of it, we can control the generation process, and we can use it to generate anything, basically anything, and we can use it to basically optimize anything. So we have already talked about generative AI for robotics. I mentioned generative AI for messenger RNA and the vaccines. And so people can also use generative AI to design, I don't know, like chips, CAD designs, or like to use generative AI to solve facility planning problems. And there are many exciting new problems out there, which or either traditional science problems or traditional OR problems, but they can all benefit from generative AI. Okay, so finally, so in Princeton, so I created a new AI center together with Ruan Adams. So so the focus of our center is try to think about opportunities of using generative AI to solve engineering problems. And we're collaborating with a bunch of like centers and institutes on campus. And we have a very, very attracting postdoc fellow openings. And we also have plenty of compute. If anyone is interested in doing independent postdoc fellow working on, I would say, AI for something, AI for X research. So happy to talk. Thank you very much.
Thanks for the great fascinating talk. Any questions for speakers? For your guided diffusion work, seems like same method has been proposed previously. It's called a diffusion posterior cell.
Yeah, so the guidance term, I think the guidance term has similarity to a few concurrent works. So our paper is mostly about thinking about this for solving general optimization problems and establishing the optimization, the sub-optimatic guarantees. So the motivation was actually to figure out, so because there are so many methods with, I would say, similar this and that method for adding guidance. So the question we really want to study is, what do they converge to? What's the limit for adding guidance for doing optimization? So that's the main message. It's the main message is there is a limit for adding guidance, and that limit is this regularized optimization problem. And if you want to do better, you want to do iterative fine-tuning with self-retraining. Yeah, very good question.
Thanks, Mengdi.